Hi, I'm Ned, and I make games. Have you ever wondered how shaders work in Unity? Or do you want to write your own shaders for the Universal Render Pipeline, but without using the shader graph? Either because you need some special feature, or just because you prefer writing code by hand, this tutorial has you covered. This is the third video in a series on HLSL shaders for URP. If you talk to shader devs, few words strike more fear into their hearts than transparency. Well, in this video, I want to demystify transparent shaders a bit. In the process, we'll learn about render queues, custom inspectors, blend modes, alpha clipping, winding culling, and double-sided normals. If you prefer written tutorials, check out the article version of this tutorial in the video description, as well as links to all the other tutorials in this series. If you're starting here on part 3, I would recommend at least downloading the starting scripts from the video description, so you have something to work from. Before I move on, I want to thank all my patrons for helping make this series possible, and give a big shout out to my next-gen patron, Groovy-Dooby-Doo. Thank you all so much. Let's delay no further and get to programming. So far, our shaders have ignored the alpha channel of the main texture, staying completely opaque. I say that it's time we change that. Transparency is a complicated topic for many reasons, but it's pretty easy to get started with it. Just add one line to your pass block. This blend command determines how the rasterizer combines fragment function outputs with colors already present on the screen. The color returned by the fragment function is called the source color, while the color stored on the render target is called the destination color. The rasterizer multiplies each color by some number and adds the products together, storing the result in the render target and overriding what was already there. You can specify these multipliers using the blend command. First, the source color multiplier, and then the destination color multiplier. Blend 1, 0 results in a fully opaque material, the default. For transparency, we need to linearly interpolate between the source and destination colors, based on the source color's alpha. Thankfully, ShaderLab has a source alpha and 1 minus source alpha multiplier that's perfect for this goal. Add this line to your forward lit pass block. In the scene editor, test out blending by lowering the alpha of your material's color tint, or slotting in a texture with an alpha channel. Unfortunately, it doesn't take long to notice some issues. First, transparent objects don't always blend with the objects behind them. Remember the depth buffer from our discussion on shadow mapping? Currently, the rasterizer stores transparent objects' positions in the depth buffer, preventing fragments behind them from ever running. We can't blend colors with a material that was never drawn. We need a way to prevent transparent surfaces from being stored in the depth buffer. Thankfully, this is also easy to do. Add a ZWrite off command to your forward lit pass block. This prevents the rasterizer from storing any of the pass's data in the depth buffer. Now, all surfaces behind this shader will always draw. But there's still some weirdness. The skybox completely overwrites all transparent objects due to render order, and sometimes objects even flicker depending on the camera position. The blend operation depends on the order objects draw to the render target. Objects behind a transparent object must draw first in order to blend colors with them. Thankfully, we can control the draw order using render queues. When preparing to render a scene, the URP takes a look at all renderable objects and sorts them by a render queue. There are a few queues that you can place shaders into using a queue tag, set in the subshader tags block. The default setting is geometry, which is used for opaque materials. The transparent queue comes after geometry. By placing mylit into the transparent queue, we can ensure that opaque objects draw first. There's also a skybox queue, which runs in between geometry and transparent. Previously, the skybox rendered after mylit, and since mylit had ZWrite off, the rasterizer allowed the skybox shader to override it. Using the transparent queue, we can avoid this issue. For debugging and a few other more advanced systems, Unity also has a render type tag. This should be set to either opaque or transparent. Render type doesn't affect render order, but go ahead and set it for now. Now, both transparent spheres should show up in front of the skybox. Notice that the spheres even draw over each other correctly. Knowing what we do about render order, you might guess, correctly, that URP sorts objects within the same queue by the distance from the camera. back to front, or farthest to nearest. This is crucial for transparent shaders. Unfortunately, this sorting does not extend to triangles within a single mesh. If you have a mesh with many pieces that overlap, they might overwrite one another. The only reliable way to fix this is to break your mesh into many pieces. Just one of the many headaches that you must endure when working with transparent materials, unfortunately. Before moving on, take a look at the frame debugger. You can see render order and verify that each object is in its correct queue. Look under Draw Transparent Objects for your transparent materials. If for some reason you need to tweak the draw order on a material by material basis, every material has a queue field at the bottom of its inspector. You can change this material's queue and even give priority to certain materials. For instance, the Geometry +1 queue runs after all other objects in Geometry, but still before Skybox. There's one more bug that you might have noticed. Transparent objects cast fully opaque shadows. Transparent, also known as partial shadows, are very complicated, and I will not be covering them in this series. For better or worse, the Lit shader does not even support them. The best that we can do is disable shadows for transparent objects, but in order to do that, we need to set up some C# infrastructure. If you wanted, you could use this shader for opaque materials like before, set the tint to full alpha, and then use a fully opaque texture. However, this is hardly an optimal solution. Since we turned ZWriting off, there would be no protection from overdraw. In addition, the queue and render type are also incorrect. Is there a way to change the Z-tests mode and tags using material properties? Well, yes, but we'd have to remember to set them all correctly in unison. Thankfully, there's an easier way. Let's create a custom material inspector script to easily switch between opaque and transparent modes using a single drop-down menu. Unity editor scripts are placed in a folder called Editor, so create that first. Then, inside, create a C# script called mylit custom inspector. Open it and delete the start and update functions. Change the mylit custom inspector to inherit from shader GUI, which is located in the Unity editor namespace. There's a lot to know about editor scripts, but we only need to use a couple key features here. First, override the onGUI method, which Unity calls whenever it needs to draw a material inspector. We can get the currently viewed material using the target field of Material Editor. Before going any further, set up some properties in the shader file. Properties don't only store values used in HLSL code, they can also store metadata about a material for our inspector to use. Create a float surface type property to remember if this material is opaque or transparent. Add a hide in inspector attribute to ensure that this property doesn't show up in the user-facing inspector. Next, create 3 float properties for the source blend, destination blend, and ZWrite modes. To direct ShaderLab to use a property value in the blend and ZWrite commands, surround the name with brackets. Do this in the forward lit pass. The Shadowcaster pass can use the default values of blend10 and ZWrite on. Now we need to change the queue and render type tags. Unfortunately, pure ShaderLab doesn't support variable tags. We'll take care of this in the C# inspector. For now, reset the render type to opaque and remove the queue tag. It will default to geometry. Return to the custom inspector class. Create an enumeration containing all surface types that we'd like to support, opaque and transparent. Then, to add a dropdown containing all values in this enumeration, call Editor GUI Layout enum popup in onGUI. The first argument is the UI label, and the second argument is the current value. The material stores the current value in its surface type property. However, it's not a good idea to read it directly from the material. In order to support serialization, undo, and various other editor functions, Unity provides a material property class. It passes a list containing a material property instance for each property in this shader. Use the findProperty method to pick the one corresponding to surface type. Material property stores values as floats, but it's really easy to cast them as a surface type enum. Pass that as a second argument to enum popup. Enum popup returns the value displayed in the popup, either what was passed in or a new value that the user selects. Either way, cast that back to a float and reset the value in material property. Now, to listen for user input and set material properties appropriately, surround enum pop-up with these begin and end change check functions. End change check returns true if the user picks a new value from the dropdown. Next, create an update surface type function, taking the material as an argument. Call it inside the end change check block. Update surface type will refresh the ZWrite mode, blend modes, tags, and shadowcaster based on the surface type property. Since the function runs post-input, it's safe to read properties directly from the material. Use a switch statement to refresh the material based on the surface type enum. Set the render queue using material.renderQueue. Override the render type tag using a setOverrideTag method. Set the ZWrite and blend properties using setInt. There's a handy enumeration from Unity for blend modes. Include the unity.rendering namespace to access it. As for ZWrite, 1 corresponds to on and 0 to off. Lastly, to turn off shadows, we can just disable the shadowcaster pass. The material class has a setShaderPassEnabled method to handle this. Finally, back in onGUI, ensure a base.onGUI call comes at the end of the method. This draws the default inspector, which includes all properties of your material without the hide and inspector attribute. All that's left to do is register the inspector class to our shader. In the .shader file, use the custom inspector command inside the shader block to do this. Okay, check it out in the scene. You can now easily switch between opaque and transparent mode. You should verify that everything looks good in the frame debugger too. You might notice one issue. If you switch shaders, the material might not initialize correctly until you mess with the surface type dropdown. The shader GUI class has a callback when a new shader is assigned to a material. Assign new shader to material. Override it and leave the base call at the top. Check if the new shader is the mylit shader using its name field. If true, call update surface type. Another bug squashed. Is there any way to combine the flexibility of a transparent material with the performance of an opaque one? Well, sort of. There's another common transparency strategy called alpha testing, alpha clipping, or alpha cutouts. In this mode, we use a texture like a cookie cutter to render only certain parts of a mesh. It's really a hybrid mode. Each fragment is either fully opaque or fully transparent. No blending is required, making it safe to write to the depth buffer and to cast shadows. Supporting cutouts requires small adjustments to just about all code that we've written so far. Let's start with a custom inspector. Add a transparent cutout member to the surface type enumeration. While we're there, rename the transparent mode to transparent blend, just to be more clear. In update surface type, we need to set everything up for cutouts. They have the same blend and ZWrite modes as opaque surfaces, but a different queue and render type tag. They also can cast shadows. Reorganize the switch statements to take all of this into account. Notably, cutouts should run in a new queue called alpha test. This queue runs after geometry but before skybox. But since cutouts don't blend, why not use the geometry queue? It's a question of optimization. Beyond enabling transparency, draw order is a powerful optimization tool. Imagine this situation. Two objects have opaque shaders, but one is much more resource intensive. We'd like to minimize overdraw to prevent shading the expensive material when it's not visible. Unity tries to achieve this with depth sorting, but it's not always completely reliable. By placing the expensive shader into a later queue, we can ensure that it's drawn when more of the depth buffer is filled. Alpha cutouts are more expensive than opaque shaders, so Unity orders them later to save time. But back to the code. In mylit_litPass.HLSL, we can utilize the clip HLSL function to do the work. If you pass it a number less than or equal to 0, it will discard the currently running fragment. What does that mean? Discard is a command to the rasterizer, causing it to pretend like it never invoked a particular fragment function. It will short-circuit the fragment function, returning immediately after clip, and throwing out all data pertaining to the fragment. it will neither write to the depth buffer or the render target. It's as if the fragment function was never called. We want to clip this fragment if the alpha value is less than a threshold. Let's use 1/2 for now. Subtract the alpha component by 1/2 and pass that to clip. To apply the color tints alpha, multiply it with the texture sample as well. Go ahead and try all of this out. Grab a texture with an alpha channel and change your material to transparent cutout mode. It's looking pretty cool, but there are several things to fix. Let's start with the easiest. Right now, we always clip pixels below 50% alpha, but that might not be appropriate. Let's add a property to make this adjustable. Define an underscore cutoff float property in the shader file. It should always range between 0 and 1, so we can use this special range property type to create a slider in the inspector. By the way, this property has a magic name, meaning Unity always expects the alpha cutout threshold in a property named cutoff. This will be important later on, like when we look at baked lighting. But for now, just make sure that your property is named cutoff. Then, in mylit forwardlit pass.HLSL, define the cutoff variable near the other properties, and subtract cutoff from the alpha in the clip function instead of 0.5. Now you can edit your material to better match the alpha values in the texture you're using. On to the next problem. We're clipping even in blended and opaque materials. This is not only incorrect, simply having a clip function in your shader can drastically decrease performance. We should use a keyword to remove the clip line when in opaque or blended modes. This will be the first time that we've actually used a keyword to change our own code. These keywords don't have a value, not even true or false, so a #if block cannot parse them. Instead, test if the keyword is defined using the defined function. A keyword is defined when it is enabled, and it is not defined if it's disabled. There is a shortcut for this, #ifdef. Keep in mind that there's not a #elifdef for whatever reason, so sometimes I still use the entire defined syntax for clarity. Anyway, we'll use the alpha cutout keyword to include or omit the clip function. Wrap the clip call in a #ifdef block, and we're good to go. It's possible to enable and disable keywords from C#, so we can take care of this in the custom inspector. In update surface type, enable or disable alpha cutout based on the surface type. Now, we need shader variants based on alpha cutout. Moving to the .shader file, add a #pragma to generate them. Instead of multi-compile, use a shader feature local command. Shader features are just like multi-compiles, in that they generate shader variants based on a list of keywords. The difference comes in game builds. When you build your game or create a distributable, Unity must determine which compiled shader variants to include in your build. It gathers all shaders used by the game and starts filtering shader variants. Unity includes all variants generated by multi-compile commands, but before including a shader feature variant, it checks to make sure that some material in your game has the required keywords enabled. For instance, Unity only includes mylit variants with alpha cutout enabled if a material has a cutout surface type, and thus we enable the alpha cutout keyword. Since this check happens at build time, keywords that change dynamically at runtime, like the URP lighting keywords, should use multi-compile. Otherwise, use shader feature. Why bother with all this? Well, shader variants are not cheap to compile. Shader features help optimize build time. The bigger your game gets, the more important this is to think of. Also, shader features always have an implicit underscore in their keywords list. In other words, they always trigger a variant with none of the listed keywords enabled. Of course, that variant may or may not be used by your game, but Unity is ready for the possibility. Finally, the local suffix indicates that the keyword is unique to this shader and will not be set globally. We set alpha cutout on a material by material basis, so it can use local variants. Keywords set globally by URP, like main light shadows, cannot be local. Unity has a hard limit on the number of global keywords it can support, so it's a good practice to use local variants whenever possible. With all that done, your shader should look the same as before, but your FPS will thank you for this optimization. The next bug to tackle is shadows. Objects no longer cast shadows that match their cutout shape. To fix that, clip fragments in the shadow caster pass. First, let's take the alpha clipping logic in mylit forwardlit pass.HLSL and move it to a function called testAlphaClip. Pass the color texture sample as an argument. To make this available in mylit shadowcaster pass.HLSL, we should add it to a separate file and hash include it in both of our pass files. Create a new mylit common.HLSL file. Remove testAlphaClip from mylit forwardlit pass.HLSL and paste it here. TestAlphaClip requires a couple of properties, tint and cutoff. Properties are defined shader-wide, so it makes sense to move property definitions to the common file as well. Finally, include the URP library to have access to the Texture 2D macros. In mylit forwardlit pass, trim duplicated code and add the include line to bring in our common code file. Before moving on, let's take a moment to think about this. HLSL is very C++-like, so hash include causes the compiler to literally copy and paste the contents of the common file onto this line. What happens if we accidentally include a file twice? Unity will throw an error saying that a variable has already been declared. Okay, but duplicating include lines is not that common. What if mylit common and mylit forwardlit pass also include a file called mymath.HLSL? Then my math would be duplicated. To simplify things and prevent errors, it's customary to wrap all code in an HLSL file inside something called a guard keyword block. First, check if a keyword is not defined. That's what #if_indef does. It's shorthand for #if not defined. On the very next line, define the guard keyword. Don't forget a #if at the end of the file. Now, the first time mymath is included, the guard keyword is defined. The second time, the guard keyword is defined, so it skips the code inside. Go ahead and add guard keywords to mylit common. I usually add them to all HLSL files just to be safe. After all of this cleanup, your shader should still look the same. Let's finally add clipping to the shadowcaster. First, in the shader file, add the alpha cutout shader feature to the shadowcaster pass. In mylit shadowcaster pass.HLSL, add #include mylit common.HLSL. At the moment, the shadowcaster has no support for UVs to sample the main texture. We'll need to pass them all the way to the fragment stage. To do that, add a UV field to interpolators. Each field here is another that the rasterizer has to interpolate, and it's best to keep this struct as small as possible. Surround the UV field with a #shift block, ensuring that it's only interpolated when needed. It's not as important to do this in the attribute struct, but it can't hurt. In the vertex function, transfer the UV to the output struct, again only if alpha cutout is defined. Then, in the fragment function, sample the color texture and call testAlphaClip. We can wrap all of this in a if block too. Remember, clip discards a fragment if passed a value below 0, causing the rasterizer to throw it out and not write to the depth buffer. Since the depth buffer becomes the shadow map, clipped fragments won't show up there either. With that, your shadows correctly match the clipped shape. Make sure you test out all modes on your material to make sure that the if blocks are set up correctly. There is one last problem I want to fix, but it requires a little more explanation. Often, games use alpha clipping on flat planes, in which case everything looks okay. But if you turn on alpha clipping on a sphere, you might notice that the inside becomes invisible. This is another optimization technique called face culling, winding culling, or often simply just culling. The particulars aren't that important for us, but basically the rasterizer determines whether it's rendering the front or the back face of a triangle. The back face is usually on the inside of a model, so the rasterizer culls it, or decides not to render it. If you've ever had weird issues importing from Blender and had to reverse faces, culling is likely the culprit. In our case, we'd like to render the inside of the sphere. Luckily, it's easy to turn off culling. In mylit.shader, add a new float property called cull. We'll use this to set another ShaderLab command, also called cull. Cull can take 3 different values: off, front, and back. Off completely turns off culling, while the other 2 cull one side of a triangle. Unity has a C# enumeration for these options, and we can instruct the default material inspector to create a dropdown using it. In the enumeration, back has an int value of 2, so set that as the default. Then add a cull command to the forward lit pass and the shadowcaster pass, with the cull property in brackets. Okay, but there's a new bug. The lighting is incorrect. Notice that both sides of a triangle receive the same amount of light, as if it was made of paper. This is because both sides have the same normal vector. It is not automatically flipped for the back face. We'll have to do that ourselves. In mylit_forward_lit_pass.HLSL, we can flip the normal vector given to input data if we're rendering the back side of a triangle. To flip a vector, simply multiply it by -1. But how can we know which side of a triangle is currently rendering? The rasterizer has this information and makes it available through a special fragment stage only semantic. To gain access to it, simply add another argument to the fragment function. Both the exact semantic and the argument type depend on the current platform. Unity provides macros to sidestep this compatibility issue. Regardless, front face's type is essentially a Boolean, true if the triangle front face is visible. Unity also provides another macro to choose a value based on the front face, like the ternary operator in C#. Use that to either multiply the normal vector by 1 or -1 before setting it in lighting input. So that fixes lighting, but the triangle back face now have shadow acne. Since shadow biases also depend on normals, we need to flip them too. Unfortunately, the rasterizer front face data is not available in the Vertex stage, which runs before the rasterizer. Luckily, there's another way. If we assume that the normal vector should always point roughly towards the camera, we can flip it if it does not. Let's try to keep the angle between the normal vector and the view direction to less than 90 degrees. If the angle is greater, flip the normal vector. This will bring it back within an acceptable range. There's a very simple function to find the angle between 2 vectors, the dot product. It returns the cosine of an angle. Cosine of 90 degrees is 0, so if the dot product is less than 0, the angle between the vectors is greater than 90 degrees. Let's implement this in mylit shadowcaster pass.HLSL using a new flip normal based on view direction function. Pass it the position and normal. Calculate the view direction using this built-in URP function, which we also use in the forward lit pass fragment function. Then, only if the dot product of the normal and view direction is less than 0, multiply the normal by -1, then return the normal. Modify the clip space calculation to call flip normal based on view dir. Back in the scene editor, it looks like there's no more shadow acne, so mission accomplished. This technique isn't perfect. Sometimes it creates shadows that kind of flicker as you rotate around an object, but that's usually preferable to shadow acne. Double-sided normals are not free. Both the flipping operations and the front face semantic have a bit of overhead. It's a good idea to use a keyword to turn it on and off. Thinking about this, there's also no reason to ever flip normals if culling is on. This leaves only 3 useful configurations: back culling, no culling, and no culling with normal flipping. Let's address these concerns by updating the custom inspector. Create a new enum, face rendering mode, to encapsulate the aforementioned modes. Similarly to the surface mode, we can use another hidden property to keep track of this setting. In onGUI, add another enum dropdown controlling this new property, face rendering mode. In update surface type, we need to update the cull property and either enable or disable a keyword, double-sided normals. If the face rendering mode is front only, set cull to back, using Unity's cull mode enum. Otherwise, turn culling off. Then, enable or disable the keyword appropriately. Moving on to mylit.shader, first hide the cull property in the inspector and remove the enum attribute. It's handled by code now. Second, add another hidden property for face rendering mode. Third, add a shader feature for double-sided normals to both of our passes. In mylit forward lit pass, wrap all the normal flipping code in if blocks. There's a bit of trickery to hide the front face semantic in the argument list. It's ugly, but it does work. In mylit shadowcaster pass, similarly, wrap the call to flip normal based on viewdir within a #if block. In the scene editor, try out different face rendering modes to make sure everything works as expected. In the future, think carefully whether an object actually needs any of these options. Turning off culling can dramatically increase performance cost, and double-sided renders aren't exactly cheap either. These options are very useful for things like foliage, just don't blindly enable them for all materials. And with that, I would consider this a fully functional shader. It supports all the basic needs: textures, lighting, shadows, transparency, and even goes above and beyond the lit shader with double-sided normals. But of course, we're far from done. In the next tutorial, I'll focus on more surface options. We'll implement a new lighting model called PBR, or Physically Based Rendering. Rough, metallic, glassy, smooth, shiny, and glowing materials are in our future. For reference, here are the final versions of all the shader files after completing this tutorial. You can also view them on GitHub from a link in the video description. Please stay tuned, subscribe, and press the bell to be notified when my next tutorial video goes live. If you enjoyed this video, consider liking it as well. It really helps out with the YouTube algorithm. Are you having any issues or questions? Feel free to leave a comment or contact me on any social media. I do read all comments and I'll reply as soon as I can. I want to take another moment to thank all of my patrons for helping make this video possible, and once again to give a big shout out to my next gen patron, Krooby-Dooby-Doo. Thank you all for your support. It really does mean a lot to me. And if you would like to download the example shaders from this tutorial and all of my others, consider joining Patreon too. Thank you all so much for watching, and make games!